Okay, so welcome everyone to today's Corking seminar. We are happy to have Adele Padgett here today, and she will speak about an omitable definition of the complex gamma function. Please.
Yes, thank you very much for the invitation to speak. So I'll start by saying a little bit about ominomality and about the gamma function in order to explain what it would mean to have an ominable definition of the complex gamma function. And then I'll explain my theorem with Patrick Speisiger. So I put theorem here in quotes because this is sort of an imprecise statement, and I'll give the precise statement later. But we show that the gamma function, the complex gamma function, restricted to certain unbounded domains in the complex numbers is ominimal, is definable in an ominimal structure. And I'll explain what that means. And then I have an application, which is to construct derivations that respect the gamma function on its natural domain in the complex numbers. And so this is, I'm speaking about this because this is what I wrote in my abstract, although unfortunately, as I was preparing the talk, I realized that I don't need the full strength of the theorem to do this application, but I still hope it's interesting, and I'll still speak about both these things together. And I'll explain why the full strength of this theorem with Patrick is not needed. So I'll start by saying a little bit about the gamma function. So gamma is a meromorphic function, and it's holomorphic on the complex numbers minus the non-positive integers. And this picture on the right is a domain coloring for gamma. So the dark regions represent areas where the gamma function has small modulus, and then the lighter region on the right is where gamma has larger modulus, and the colors represent the argument. So you see here where there's like a constant where there's a constant, sorry. Okay. I just want to show. So here there's a constant like red color that changes from red to lighter red as you go toward the right. That represents that the gamma function has argument 0. And so red means argument 0 because the gamma function is real on the positive reals. And then as you move up to the right, you cycle through a rainbow. So that represents going around the unit circle. So you're cycling through all the different arguments and then coming back to red, which is argument 0 here. And then you could maybe keep going through more rainbows. So you keep going around the unit circle. So I'm explaining this because I'll use this later in figuring out on what kinds of domains in C the gamma function could be ominimal. And I'll explain what that means also. So, and then I also wrote down 2 functional equations that the gamma function satisfies. So first, gamma of z plus 1 is z times gamma of z. And so the reason why the gamma function is important is because it extends the factorial to complex numbers. So gamma of a positive integer n plus 1 is n factorial. So that's one of the properties of the gamma function. And then here, the second equation, this is more complicated, but essentially what's important is that the second equation here gives a way to relate values of gamma at z plus numbers that are less than 1, so k over n, with gamma of n times z, so z scaled by n. And you get one of these equations for each positive integer n. And again, I'm mentioning these things because these are the properties of gamma that I'll use later. And then the last thing that I wrote down is that gamma of z is equal to square root of 2 pi times z to the z minus a half times e to the minus z times e to the phi of z. This is Stirling's function. And this equation is Stirling's representation for gamma in terms of the exponential function and this other function phi of z. So this is what I'll need about the gamma function. And now I want to say a little bit about ominomality. So model theory, I know there are some people who will already know this, but I want to talk a little bit about it in case there are people who maybe haven't seen this before. So a linearly ordered structure, which we write as R, I'll only be thinking about the real numbers and then the complex numbers, which we can think of as like R squared, along with some symbols, including the ordering symbol. So these are symbols of our language. So we say that this is O minimal if every definable subset just of the real numbers is a finite union of points and intervals. And so definable subsets, let me say what that means. You can have definable subsets not just of like the real numbers, but also of Cartesian powers of the reals. So for example, you can define the set of pairs x and y in R squared such that x is less than y, or things like that. So you could also define the complex numbers as R squared, or the complex field as R squared, along with the extending the multiplication and the addition. And so I also have written down here 4 examples of O-minimal structures, or actually the first one is not a non-example. So the real numbers with the ordering symbol, a symbol for 0, and the sign function is not O-minimal. This is because you can define the set of real numbers where sine of x is equal to 0. And that's an infinite discrete set of points. But in order to be O-minimal, every definable subset of the real numbers has to be a finite union of points and intervals. So this would violate the definition of O-minimality. And now I have 3 theorems that these 3 other structures are O-minimal. So first, the real numbers as an ordered field. This is O-minimal, and the theorem is that every subset of R, every definable subset of R can be defined just by polynomial and single variable polynomial equalities and inequalities, which have finitely many connected components, or defined sets with finitely many connected components. And so combining those gives you always sets that are finite unions of points and intervals. So this is O-minimal. And then Wilkie, who's here, showed that the real exponential function, or the real field with the exponential function restricted to the real numbers, is O-minimal. And then Van den Dries and Speisiger showed that the real field with the gamma function restricted to the positive real numbers is O-minimal. So today I'm going to talk about defining the complex gamma function, but it was already known that the gamma function on the positive real numbers is O-minimal. And so the intuition for O-minimality is that in order for a function to be O-minimal, well, if a function is definable in an O-minimal structure, then it can't like oscillate forever. That was the problem with sine, right? So because sine has this infinite oscillation, you can identify that with sine, you can just take its 0 set, and then you get a set that violates the definition of O-minimality. And then I also want to point out that maybe if you haven't seen the notion of O-minimality before, the definition looks pretty simple, but there have been a lot of tools that have powerful tools that have been built from it that have applications. And here I just listed Diophantine geometry and functional transcendence. So this is what I'll need to know about O-minimality. And now I want to think about the main point of my talk, which is how would you define the complex gamma function in an O-minimal structure? Oh, first let me maybe explain this picture. So this picture, the first picture that I showed on the left, shows a domain coloring for the gamma function. And then if you zoom out and look just at the upper right quadrant, then you get this picture. So you can see in this picture, if you move sort of up or to the right, that you're passing through a lot of these rainbows, which represents that you're going around and around and around the origin, and that's a form of oscillation. So it will not be possible to define the gamma function on its whole domain in the complex numbers, because that would involve some kind of infinite oscillation, and that's not allowed in all minimal structures. So then the question becomes, where would the gamma function, or on what kinds of domains would the gamma function be minimal? Where would it not oscillate too much? So maybe the natural thing is to look at one of these rainbow strips at a time. So let me sketch a few of these in, so I can sketch along curves of constant red color, even though the shading change. Oh, shoot. Okay, this is fine, right? You can see it again?
Yeah, it's fine now.
Okay. So if I sketch along curves, these curves where the color red is fixed, then gamma restricted between any two of these curves. So like for this region here that I'm shading in green, there gamma only has like one rainbow, which represents that it only goes around the origin once. So you've restricted the amount of oscillation that it can have. And so then the idea would be that the gamma function restricted to any one of these strips should be minimally definable. Well, so as I've written it, that's maybe, I don't know exactly that that's true. And that's due to the Stirling function here, or the Stirling formula for gamma, which I've highlighted in blue. So what Patrick and I do in our theorem is we define gamma using the exponential function and Stirling function. So this phi, this is Stirling's function. And the complex exponential function, it has a similar problem with oscillation. So you can't define it in an O-minimal structure on all of its domain, on all of the complex numbers, because if you go up, the complex exponential function is periodic. So you could identify some kind of oscillation and fail to be O-minimal. The complex exponential function would fail to be O-minimal on the whole complex plane because you would get some kind of oscillation. So in order for the exponential function to be O-minimal, you have to restrict the imaginary part of its inputs. So we can restrict to horizontal strips. And that bounds the imaginary part, so then you avoid the infinite oscillation. But if we're bounding the exponential function to some horizontal strip, then that causes an issue when we're trying to use it to define gamma on the whole one of these strips, because these strips go kind of infinitely far up to the left. So as I've written this now, it's necessary, or it seems like it might be necessary to cut off these strips at some point. It doesn't matter exactly how you do it, because if we would allow gamma to go infinitely far up to the left on one of these strips, we could run into a problem with the exponential function being definable, and we use that to define gamma. So this is maybe a subtle point, and it's not, we don't know that it's necessary, so it might be possible to obtain that the gamma function is definable on a whole one of these unbounded strips, unbounded to the right and unbounded to the left. But as I've written it now, I'm not sure that it can be unbounded to the left as you go up. Is that clear? This is sort of a subtle point, maybe. Okay. So then what Patrick and I show is that the real and imaginary parts of the gamma function restricted to any one of these strips cut off somewhere on the left-hand side as you go up. These are definable in an ominomal structure called RG. I won't really talk about that at all, except to say that that's where the Stirling function ends up being definable. And then also with the exponential function on some sort of on the horizontal strip. And now maybe let me speak about a little bit of the model theoretic context for this work. So like I mentioned, Van den Driest and Spijsiger showed that the gamma function restricted to positive real numbers is definable in an ominomal structure. It's definable in this RG ominomal structure. What they really proved is that the Stirling function restricted to the positive numbers is definable. And then they add the exponential function to obtain gamma on the positive real numbers. It was also already known that restrictions of gamma to many bounded subsets of the complex numbers are definable. That's in a different ominomal structure called Rn, which again, I won't talk about really. N stands for analytic functions, restricted analytic functions. And also Tobias Kaiser and Patrick, they studied when functions definable in a different ominomal structure, Rn with the exponential function. They studied when functions definable there in that ominomal structure have holomorphic extensions. But none of these things cover the case that we proved in this theorem at the top, that the gamma function on some unbounded domain is definable in an ominomal structure. And so why did we do that? Why, if you have all these other results about the gamma function on real positive real numbers or on bounded domains, why would you want to have the gamma function definable on some unbounded domain? What would this gain you? Well, my motivation for this was to try to prove an actionual theorem for gamma. And the actionual theorem for the exponential function is a theorem about functional transcendence. And so by actionual for gamma, I mean some kind of version of that for the gamma function. So something about the functional transcendence of gamma. And for this hasn't been proved, but it's something I'm thinking about now with Sebastian Etarovich and Roy Zhao. And we expect, or we're trying to use, there's a standard ominimal proof strategy for proving versions of the actionual theorem for different kinds of functions. And it uses a kind of point counting. Oops. And in this case, in order for it to make that point counting argument work, we expect that we probably need the gamma function to be definable on unbounded domains. And I'm saying probably because I also thought that in the application that I want to talk about today about constructing derivations that respect the gamma function, that I would need to have the gamma function defined on some kind of unbounded domain. But that turns out not to be true, as I realized as I was writing the talk, because of a special property of the gamma function.
Adele, sorry, would you mind spelling out what the actionual statement would be for gamma?
Yeah, so Sebastian Etarovich and we state this in our paper, and it looks similar to the statement for the exponential function. So the exponential function, let me maybe try to write it out. Just a second here. I'm looking it up in our paper just to make sure that I copy it out correctly.
I'm sorry, I didn't mean to distract you too much. So.
No, it's okay. I'm gonna write it out and then
Right.
I'll show it to you in just a second. So if you have holomorphic functions f such that fi is not like some rational number, this is kind of the condition that you would need. Then you can say that the transcendence degree of over C of these functions and gamma of all these functions should be at least n+1. This is like kind of a weak X-annual statement. But the idea is that the only algebraic relation that gamma should understand is, let me go back up here, is this one. So gamma of z+1 equals z times gamma of z. Gamma also satisfies other functional equations, but for example, this other one, the second one that I wrote down here, this involves the exponential function. So there shouldn't be much to say about this if we're only thinking about gamma. Gamma also satisfies like a reflection function, but that involves sign, and so there also shouldn't be something like about that coming up. Does that clarify?
Yes, thank you so much.
Okay. Right, so this was my motivation. Proving some kind of X-annual statement for gamma is my motivation in to prove this theorem with Patrick, that the real and imaginary parts of gamma are definable in an O-minimal structure on some kind of unbounded domain. And now I want to talk about the application to constructing derivations that respect the gamma function. So this is a general O-minimal thing that comes that was first done by Wilkie. So if you have the real numbers as an ordered field, and you add in some new function symbols, so these are this is a collection of holomorphic functions. And if the structure you get when you add in these functions, which maybe have restricted domains, is O-minimal, then there are derivations on the real numbers, on all of the real numbers, that respect the real and imaginary parts of those functions in F, the collection of functions, on their domains. So then, what does it mean for a derivation to respect a function? Well, we say that a derivation respects a function f, first just of a real variable. If the derivation of f of x is equal to f prime of x times derivation of x for all x in the domain. And then you can build this up to partial derivatives and or partials and derivations on the complex numbers using Cauchy-Riemann equations. And the Wilkie also shows that these derivations on R, if you take pairs of them, then you can show that these correspond to derivations on the complex numbers that respect the functions in this collection on their domains. And the way that he does this is using the Cauchy-Riemann equations and Schwar's reflection. So I think I won't have time to talk about how these derivations are constructed, but I just want to say maybe how you get that they respect these functions, because right now what Wilkie does is he shows that there are derivations that respect some collection of functions on the domain in which they're definable in an minimal structure. So in our case, if we want this collection to have the exponential function on some strip and the gamma function on that first strip, so the one in this picture that I've highlighted in green, then when we start, at first, we only know that the derivations respect our functions here on these restricted domains. But you can actually show that these derivations respect the functions everywhere. So I'll do the calculation for the exponent for x. So if you have some complex number whose imaginary part is bounded between 0 and 2 pi, then the derivation of x of this complex number plus some multiple of 2 pi I is, well, because of the periodicity of the exponential function, this is the same as the derivation of x of z. And now, since z is in this strip where we know that derivations respect gamma, this is equal to x of z times the derivation of z. And then again, using periodicity, x of z is the same as x of z plus 2 pi I n. And then it's a property of the way that the derivations are constructed that 2 pi I n is in the field of constants. So the derivation of z is equal to the derivation of z plus 2 pi I n, because the derivation of 2 pi I n is a 0. So using the periodicity of the exponential function, you can calculate that, well, as soon as you know that the derivations respect x on some horizontal strip, they actually are going to respect x everywhere. And we want to do something similar for the gamma function, but this will use properties of the gamma function in the same way that the calculation for x uses its periodicity. So maybe let me look first at the second equation here. Gamma of z plus 1 is z times gamma of z. So if you have some complex number z0, where you know that the derivation respects gamma at z0, so this is equal to gamma prime of z0 times derivation of z0, then using this equation, you can run the calculation to show that the derivation also respects gamma at integer shifts to the left and right of z0. You just do the calculation and show that that holds. So you can imagine if you have some region where your derivations respect gamma, you can shift that whole region to the left by integers and to the right by integers to get kind of like a strip, a whole strip where your derivation respects gamma. And then using this first equation, which is, I know it's like complicated to look at, but what's going on is that you're relating the values of gamma at z plus numbers that are less than 1 with a gamma of some scaling of z. So if you know that your derivation respects gamma at some number z0 plus k over n for all k from 0 up to n minus 1, then you can use, again, you can do a calculation. Also, since we know the exponential function is respected everywhere by the derivations, to show that your derivation respects gamma at n times z. So using the second equation, this one, if you know that your derivation respects gamma on some region, you can extend the region, that's like with at least 1 or something. You can use that equation to get some whole strip where your derivation respects z. And then using the first equation, you can scale that strip up to get that your derivation respects gamma on some, basically on the whole upper half plane. Going back to this picture, you can think of taking the strip that I've highlighted and then shifting it to the left and right by integers and then scaling it up, and you get that get the whole upper half plane. And then using this final equation, once you know your derivation respects gamma on the upper half plane, you get also on the lower half plane. And so that gives you that your derivations will respect the gamma function everywhere. And just one final note. Or okay, I guess I'll just stop there. I'm out of time.
All right, thanks you so much, Adele, for this very nice talk. Do we have any questions or comments? You can just unmute yourself and ask, or if you prefer, you can also just type in the chat. So I was wondering, could you say a little bit more about, I mean, I guess you didn't somehow on purpose didn't want to say anything about this RG, but could you say something about this or minimal structure RG that you mentioned?
Yeah, so RG, these, maybe I'll go up here. So RG it's an O-minimal structure that comes from what are called multi-summable functions. So for example, the Stirling function, you can show that this is defined on, actually, I guess it's really the Stirling function composed with 1 over z that we work with. So this is defined on sectors like this. And then the multi-summable functions take these kind of functions, which are defined on these sectors in a specific way. And they say that if you have a multi-summable function, or this would be like a one-summable, so it's particularly simple kind of function because it's defined just on a sector and not some kind of generalized polysector thing. If you restrict your function that's defined on some sector like this to just the real numbers, then all of those functions are in this O-minimal structure are G. And so there's a definition of what it means to be multi-summable or one-summable. And then you get a whole class of functions that are definable. And it helps, yeah.
Okay, thank you. So there's one question in the chat. Maybe I'll read it out loud. So any comments on the case if its domain is suitably restricted to make it O-minimal? So I guess it's
Right. So if you restrict the domain of the sine function to some, so the real sine function is the one I mentioned, to like a bounded interval, then that is O-minimal. And that's O-minimal either in the structure RG or also in the structure Rn, which the and stands for restricted analytic functions. So the sine function on some bounded interval is a restricted analytic function. And so that would be definable in this O-minimal structure.
But excuse me, but what about unbounded regions for the sine?
Oh, so the sine, if you allow its domain to be unbounded, then you get the same problem where you can look at its zero set, and its zero set is infinitely many discrete points.
Right, but I mean the technique that you extend the gamma O-minimality to unbounded domains, even if restricted, can that be applied to other functions?
Oh, right, yeah. So if you look at the complex sine function, and you look, I guess it would be like vertical strips, right? Then that should be just fine. That should be definable already if you have the restricted sine function and the exponential function.
Okay. Thank you.
Could I ask a question?
Sure.
Can you hear me? Yeah.
Yeah.
Very nice talk, Adele. My original motivation for constructing the derivations was to actually characterize the complex definable functions that were definable in the original O-minimal structure. And this all came through model completeness of the reals, and it translates more or less to a kind of model completeness in some sense for the complex structure. Now, does your derivation respecting gamma give you a characterization of all the holomorphic functions that are definable in the real structure with gamma? Is it the same thing? Are they just the functions you get essentially using the implicit function theorem? Is that clear what I mean? Yeah, suppose you just take the real field with X and gamma restricted to the positive real axis, real line. What are the complex definable functions in there, or even just the restricted ones? Are they simply the ones you get via the implicit function theorem applied to gamma and X?
Yeah, that's a good question.
That was what the paper you quoted in mine. Right. That's why I wrote that paper, to prove that for Rn essentially.
I guess I'm not sure, but it seems so. If you have gamma or and X just on the real line, then
well, maybe it's not model complete. Is that correct? I don't know.
I would, well, okay, I don't know either, but I would kind of think maybe,
Well, you have to add the derivatives at least. I would
yeah,
think.
right.
Yeah.
But then, so if you add the derivatives, but still, I mean, yeah, then there are, yeah, I guess I'm not sure. I'll think about it.
Yeah. Well, you would get the phi function, wouldn't you?
You could define, yeah, you could define
Yeah,
phi.
but that existentially, I guess, anyway. So that's all right.
Okay. Yeah.
Yeah.
Mhm.
Charlotte, did you want to say something?
Sorry?
Sorry.
So
Yeah.
just see your hand is raised.
Yeah. So thank you for the nice talk, Adele. I was wondering, it's connected to William's question. If you could say something about the Riemann zeta function with
yes.
your results with gamma.
So actually, the only reason why I didn't mention, so Patrick and I realized that our calculations or our strategy for showing that the real and imaginary parts of gamma are definable in a no-minimal structure. The same kind of argument also works for the Riemann zeta function, and actually it's easier in that case. So the Riemann zeta function on the real numbers is definable in a different O-minimal structure called Rm star. So it's easier in that structure to show that the real and imaginary parts of zeta composed with the log function are definable. And then the reason why I didn't mention it is because I haven't yet worked out on what kind of domain, what the domain actually looks like, where you would get that the real and imaginary parts of zeta are definable. So that's, I just haven't quite done that yet. But it should still be, you should, our calculations so that you do get some kind of domain where the real and imaginary parts of zeta are definable. I haven't worked out what it looks like yet.
Okay, any other questions, comments?
May I ask, how far are we from having an Ax-Shanuel theorem for gamma?
Yeah, right. So I think probably in order to have an Ax-Shanuel theorem, you would want these strips to be unbounded in this upper direction. And so as I've written out Stirling's formula here, I have a term that's like x of minus z. But if you combine this together, right, you get x of something else. And so you would want to show that somehow you don't actually, it's not actually a problem that these strips go infinitely far up to the left. And so you can have the full unbounded strip. But again, that's something we're still working out. So if that's true, then there are still challenges, right? Like how do you, so you have to come up with a family of varieties. And it's not clear, in this case, the natural way to do that, you get a family of varieties that's definable, but not algebraic. And so then in doing the induction, that's like another problem that has to be dealt with. So there's two barriers right now.
Thank you.
All right, so if there's no further questions or comments.
I have maybe a quick question.
Sure. Mm-hmm.
Yeah, thank you for the talk. And I was wondering if there are any, I mean, this Ax-Shanuel was mentioned, if once there is an Ax-Shanuel for the gamma function, if there are any arithmetic, geometric applications in mind. I mean, I know very little about this, but if there's anything in that direction.
So this final thing comment that I was going to make at the end is about a connection between the original X-Shanuel theorem, which is for the exponential function, with number theoretic transcendence. So if you have some counterexample to Shanuel's conjecture, the regular Shanuel conjecture for the exponential function of minimal length, which means that you have, but the transcendence degree over Q of these numbers and their exponentials is strictly less than the linear dimension, the Q linear dimension of the numbers, then that means that every derivation, then every derivation that respects X would vanish at A1 up to AN. And so this uses the X-Shanuel theorem, and you also can get a much more explicit description of the field where every derivation that respects the exponential function will vanish in terms of Khovansky systems. So this is a way to say that any potential counterexample to Shanuel lives in some countable field with a somewhat explicit description. And if there was an X-Shanuel theorem for gamma, then you would be able to run a similar kind of, or I believe that you would be able to run a similar kind of argument. And you'd have an analogous version of Shanuel's conjecture also for a conjecture about number theoretic transcendence of values of the gamma function.
Thank you.
All right, then. If there's no further questions or comments, let's thank Adele again for this nice talk. Yeah. So, and yeah, I'm looking forward to seeing everyone next time. Have a good weekend.